So section 1.8, we're going to continue our discussion about exponents. Last time we started, or 2 class periods ago, but in 1.7 we started an intro to exponents. And today we're going to take a look at some properties of exponents and then using those properties. So we first have 7 properties that I'm going to show you. I'm also going to talk about briefly why each one of them is true, because it's not just magic. All right, so our first property of exponents talks about what happens when we have matching bases and we have exponents. The exponents could be the same, they could be different. Does anybody remember what happens when you have matching bases with exponents? You do. It's okay if you don't remember, you add the exponents. There we go. And the reason that that works, I'm just going to sort of give you a justification with an example, is because think about what happened if you had a cubed a squared. A cubed means a times a times a. A squared means a times a, which gives me a to the 5th. And how in the world do you get from 3 and 2 to 5? You add them. So that's what's happening there when you have 2 bases. They have to match. Okay, you can't just have any bases. They have to match. And then you have exponents on them. So if you have multiplication with exponents becoming addition of the exponents, what do you suppose happens when you have division? It is subtraction. So a to the m minus n. All right, again, a little bit of justification of why that's happening. So we're going to do a to the 4th over a to the 1st. A to the 4th is 4 a's. A to the 1st is 1a. Then what can you do when you see it like this? Well, not subtract, but divide, basically, right? So a divided by a is 1. They cancel out, they reduce. It's fractions like we've been working with. That leaves me with 3 a's, or a cubed. And again, how do you get from 4 and 1 to 3? You subtract. 3 kind of looks like 1. What's different? There's parentheses. What else? There's only one base. That's the biggest difference. I know you see the parentheses, but I could go back and put parentheses here as well. I mean, that would be fine. So the parentheses are indicating that I have a power raised to a power, right? Do we remember what happens when that happens? You multiply them, m times n. And again, justification by example. Let's use that same, I don't know why I wrote e. Let's use that same 3 and 2 that I had a moment ago. So a cubed means a times a times a, right? That's what a cubed means. And then when we square something, it means you multiply it by itself, like so. And how many of them are there? There's 6. And of course, the way you get from 3 and 2 to 6 is that you multiply. All good so far? Okay, I'm absolutely never going to ask you to do what I'm doing on the right-hand side. I just feel like that I should be able to tell you quickly why it works without you having to feel like that I just did some sort of magic in front of you. There's no magic, okay? All right, this one has the feeling of distribution. It's not actually called distribution, but we sort of feel like it's, you know, sort of passing through the parentheses, kind of like what we do with a distribution property. And so we have a to the m and b to the m. And some justification. Let's say we had ab to the 3rd. Well, that means ab times ab times ab, right? And because it's all multiplication, we have the ability to move things around. It's called the commutative property, and regrouping things called the associative property. So through the use of commutative and associative properties, I can actually regroup to put the a's together and then to put the b's together like that, right? So that would give me a cubed, b cubed. So it looks like you've distributed the 3 into each of the individual bases. Number 5 is almost identical. It's actually easier to show, but you've still got this sort of distribution kind of feel to it. So you've got a to the m over b to the m. I like using powers of 3 because they're big enough to show you what happens without being so big that they're messy to work with. So we're going to do that same a over b cubed. So it means that I have a over b times a over b times a over b. And then based on what you know about fractions, that means you have on top, you're multiplying across the top, you have a times a over b times b times b, which would be a cubed over b cubed. All good? Okay. 2 more. Does anybody remember what raising to the power of 0 does? 1. There is a caveat to this. The a itself cannot be 0. If 0 is raised to the 0 power, that's considered an undefined value. Just so you know, we're not encountering it, but there is a condition for this. So let me actually talk about why that one works, because that's the most interesting one to show you why it works. So a to the 0 could be written, I mean, there's no reason you would necessarily do so, but you could write it as a to the m minus m. Does that make sense? M minus m is 0, so those exponents match. So this would be another way of writing it. Weird, but actually correct. And if we used our property number 2 going backwards, that would mean I have a to the m over a to the m, right? It's backwards from where the property was sort of how it was stated, but it's true. What happens anytime you divide something by itself? Yeah, it reduces, right? Divides out, it cancels, whatever language it is you're using, it simplifies to the number 1. Now you can see very quickly, this actually is a legit proof, by the way. It's not a proof by example like I've been doing, where I've just sort of thrown random numbers in and said, see, it kind of works, look. This one really worked because I didn't have to specify anything special about those exponents to sort of justify it to you. But the thing that's kind of cool about this is that you can very quickly see why a can't be 0. The way that I wrote it right here, I would have a 0 in the denominator, right? Because 0 raised to any power should be 0, except for 0 raised to the 0, which is undefined. But if I had 0 in the denominator, that's a problem because that's an undefined quantity too. So a can't be 0 for this to work. Again, you won't encounter it, but it is true. Do we remember what a to the negative n is? It goes into fractions, and in particular, it goes into the denominator. So it's the same as 1 over a to the positive n. And we can actually think of it much like the last one where I did that example. This is actually a proof as well. Is that a to the negative n is actually the same thing as saying a to the 0 minus n, right? That's what negative n means. It means 0 minus n. So I can write a to the 0 then on top and a to the n on bottom. And based on property number 6, a to the 0 is 1. So that negative exponent, there's a lot of ways to sort of remember or to think about it. You can think about it as it switches things from the numerator to the denominator, denominator to numerator. It'll just alter where things are. You can think of it as doing an inverse or a reciprocal, right? It reciprocals things. I turned a noun into a verb. We do that all the time, right? It reciprocals things. But what we're really going to do is we're going to use these properties to simplify expressions. And I have, 15 examples, and they get harder as they go. So we're going to jump right into those examples and attempt to use those properties as we've defined them. So example number 1, the most straightforward one we're going to encounter, is x squared, x to the 5th, x to the 4th. And those x's are all the bases, and they match. So this is property number 1. What would we do with those exponents? Add them together. So we would add 2 plus 5 is 7 plus 4 is 11, and we're done. Okay? Really not a lot of work to show there. On the next one, you notice that we have some coefficients and we have some exponents. Depends on your level of comfort with the way that it's written. If you want, you can just deal with it where it is, and you can multiply the three coefficients together. -4 times -3 times -2. If it helps you to rewrite that, you can rewrite that. -4 times -3 times -2. And then rewrite the y's. Y squared, y cubed, y. Okay, you don't have to write that step, but sometimes it helps people, so I'll mention it. Regardless, what is -4 times -3 times -2? Yeah, 3 negatives make a negative, so it's negative, and then that value is 24. Now, whether you sort of recognized it or not, this last y has a power of 1. So be careful not to ignore the fact that it's there, even though you don't see it per se. I think I rewrote one wrong. I did. That's a 3 there. Sorry, not that one. That one. There we go. And then my y's become just like the first problem we just did. Y squared, y cubed, y1. What in the world is my new power? 7. 6. 6, sorry. Yes, 6. 2 plus 3 plus 1. So 6. Any questions so far?
So you added the exponents, you didn't multiply?
Correct, because it's property number 1.
Okay.
Same base, and I can add the exponents. Number 3, quite similar. It's got more, but it also has different bases, right? So we have to be a little bit careful. The numbers I can still treat the same way. I have 6 times 4 times 2 times 3. So if you want to rewrite, you can. You don't have to. And then I'm going to group the variables. So I've got y squared, and I've got y cubed, and I've got x cubed, and I have x to the 1. Y is first, x is first, I don't care. It doesn't matter to me in the slightest. So again, you don't necessarily have to show that, but if it helps you to regroup things, then do so. What is 6 times 4 times 2 times 3? It's 144. You're right, and you're welcome to have your calculator handy because some of these numbers will end up getting a little bit larger. I have an x and I have a y. I'll just do it in the order I've already got it listed, but if you do it backwards, that's okay. What is the power on y? 5. And on x? 4. Yeah, remember that power of 1 right here that didn't actually show up? It's not invisible, but it's there without actually thinking about it. So we have this, or you could write it as 144, x to the 4th, y to the 5th, right? That'd be another way to write that. Okay, let's take a look at another one that's very straightforward and simple. I have x squared to the 4th. So what property is that?
Number 3.
Number 3, yep. So what am I going to do with the 2 and the 4 on this one? Multiply them. And what is 2 times 4? 8. So this one is x to the 8th. Number 5. What property is number? Oh, I'm sorry. Yes.
How do you know to multiply? Because on number 2, there was parentheses, but we didn't multiply the exponents, but on 4, we did.
Okay, so one of the things that I mentioned when we were looking at these properties is that the primary difference between 1 and 3 is not parentheses. It's the fact that there's 2 bases here and there's 1 base here. So when you looked at problem number, which one was it? 2. Notice the bases repeat. There's a y here and a y here. There's an x and a y here. Sorry, that one's the one with y's. So the y's repeat, the bases repeat themselves, whereas over here, there's only 1 base. So it doesn't say x squared x to the 4th. It says x squared to the 4th. Okay? So the key idea is not looking for parentheses. The key idea is looking for multiple or repeated bases. All right, problem 5. What property do you see there? Number 3? Are you sure?
No, number 4.
It's actually 4. So the reason it's 4 is because I have 2 items inside the parentheses to a power. Okay? So on number 4, I have that sort of distribution feeling property. So if, again, it helps you, you can actually write it out. That's 4 cubed u cubed. Don't forget, the 4's cubed, right? It's not just u cubed. 4 cubed is 64. So this is 64 u to the 3rd. we good so far? Okay, most of the problems so far have just really been us saying there's one property play, right? One. But problem number 6 actually involves 2 properties.
It's 3 and 4, right?
Yeah, so I've got 3 things on the inside. That makes it property number 4. All right, there's multiple things inside. But also, one of them already has an exponent, so it's an exponent to an exponent. So don't stress. All this is telling us is that we're distributing the 3 to all of these things. 3 to the 3 would be 3 cubed, x cubed, and then y squared. If it helps you, you can just show it out, cubed.
So 27x3 y6.
Okay, so 3 cubed is 27, x cubed is just x cubed, and then y squared cubed, multiply, just like Maxwell said, y to the 6th. I know there's a lot of examples today. We're making good time though. All right, number 7. What properties do you see present on number 7?
Number 5
Number 5
is 7.
and what is 7? Don't have number 7.
Okay.
3. Yeah, it's 3. So I'm not asking you just say it, but I want you to start trying to think about what all's going on. There's more than one property here in particular. I have the division, but I also have a power b squared inside with another power on the outside. So I am going to distribute the power. So the power gets distributed to the 2. It actually, it would be probably easiest if you think about this negative as being with something. So let's call it -2. So it gets distributed to the -2. The negative's got to go somewhere. The 3 also gets distributed to the a and to the b squared. So what I really have here is -2 cubed, a cubed, and b squared cubed. Again, you don't have to show that, but if it helps, do it. What is -2 cubed? -8. That's correct. -2 times -2 times -2. A cubed is already as clean as it can get. And then what is b squared cubed? That's b to the 6th. Good job. Number 8, a little bit cleaner than number 7 actually. So this one kind of feels like the things that we were doing with fractions in the earlier sections, but now I have variables too. So when I'm looking at simplifying fractions, I have to look at like terms. In particular, the like terms here are the numbers. And then I've got like terms that are the x's. I was trying to change colors. Let's try that. The x's. And then I've got y that doesn't get moved. Okay? So we can see if 14 and 35 have anything in common. And they do. They both divide by 7. So this is 2 and this is 5. And then when I have x divided by x, what happens?
They cancel.
They cancel or reduce, simplify out. They divide.
It'd be 2 over 5y.
It would be 2 over 5y. Yes, it would. Okay. Number 9. You ready? Okay, so number 9 I can do in more than one way. And I'd like to show you both ways because there's probably one that you'll be like, oh, that one makes a lot of sense to me. And the other one where you're like, I mean, okay, but I don't really like it. Okay? You good with that? All right, so one way to deal with this is kind of like I did on the last problem where I identify the pieces that match and I eliminate what matches. So in other words, if you kind of think about this, you don't necessarily, again, have to write it down this way, but you can think of it this way. I have x squared, so that's x times x on top. I have y to the 6th, that's 6 y's. And then on bottom, I have 1x and I have 2 y's. Okay, so this is one way to think about what's there. And you can eliminate much like we eliminated the x's before. One of those x's eliminates, 2 of the y's eliminate. That leaves me with an x.
And Y 4.
And is it 5 y's? Y, 5 y's.
4.
4 Ys.
4 y's. I'm so sorry. We canceled 2 of them. I forgot. You're right. 4 y's. Okay, so that's one way to think about them. That's pretty friendly. It feels a lot like what we were doing before. Another way to think about them is to use property number 2. Property number 2 says that I can subtract exponents. So notice this is x, and then I can subtract 2 minus 1. 2 minus 1 is 1. And this is y, and I can subtract 6. Whoops. 6 minus the 2, and I would get 4. And that's another way to do the problem with that subtraction property, property number 2. X to the first, y to the fourth, or just x, y to the fourth. They're going to yield the same answer, but those are different ways of thinking about it, right? One is more property-based, one is more of an algebra elimination-based perspective. So we can do the same thing on 10. Again, I'll show you 2 different ways to do it. It's a little bit less clean in this case for the second method. So this is a U, and it's a W and a W on top. Or you have 4 U's and 6 W's. And let's see, what do you see that cancels? 1 U, 2 W's. What does that leave me with on top? 1. Yeah, so there aren't any variables left, which I think is what you guys meant when you said nothing. But this number 1 is still there, because every time we're canceling to the value 1, right? X divided by X is 1. 7 divided by 7 is 1. So when I'm reducing with this cancellation sort of marks that I'm making, I'm reducing them to be 1. So I still have 1 on top. On bottom, I have U what? To the third, and I have W to the fourth.
Does it not have to be negative?
What's that?
Does it not have to be negative?
No, 'cause it's
No.
on the bottom.
They're still on the bottom. They were on the bottom to start with. But I'm about to get something that is negative, Kenny, and you'll see what happens. Okay? All right. So let's say we're doing it like the other method, right, where we're thinking about it from property number 2, and we're subtracting exponents. So this is a U to the first. So then I would have U to the 1 minus 4, and I'd have W to the 2 minus 6. And the reason I'm writing them out is because I do want you to recognize that they are going to give you negatives, aren't they? Yeah. So if you think about this one from the perspective of those properties, I have U to the negative 3, and I have W to the negative 4. In all of your problems, you're not going to leave them with negative exponents. So write yourself a note right now that just says no negative exponents in final answers. Something like that. We're never going to leave our exponents negative. So what we would do then is we would use property number 7, that last one, that says I can take each of those and put them in the denominator and make them positive. So I have 1 over U cubed and W to the 4th. Okay? So the subtraction, the order of those things does matter. I can end up getting negative exponents.
Do you want us to show our work like that?
You don't necessarily have to show all those steps, but you need to show something of what's happening. Especially, I mean, you can see on this one, the subtraction yielded really nice numbers, but on this one, we ended up with negatives, and then we ended up having to move things. So occasionally, no work seems reasonable, but most of the time, there's going to be something you're going to show to show your thinking. Okay? It also safeguards you because that way, if you make a mistake, there's partial credit that can be awarded. Okay? All right, number 11. What fun piece do you see there?
0 X.
That 0 exponent. And that 0 exponent means what's going to happen? Yeah, everything that's raised to the 0 power, all of this will become the number 1. So this is just negative 3, exactly. Just plain old negative 3. Number 12 Very interesting. Number 12 has a negative exponent on the outside, right? Okay. So property number 7 said that negative exponents do reciprocals, correct? So it's a really good idea here if we would just do the reciprocal and make that exponent positive. A negative exponent means to do the reciprocal. It's much friendlier now because now I already have the positive exponents that I'm going to need at the end anyway. And then I can distribute to each of those pieces like we were doing before. I have 3 squared, which is 9.
Whoa, hold on.
Careful.
I'm thinking 3 times 2. My bad.
It's okay. Over 2 squared, which is 4. And in the denominator as well, I have u squared. Okay, any questions on that one? Cool. 13.
Would it just all be over 1 over all of them?
It will be in a minute. I'm going to do it in a different order than that. This actually looks exactly like property number 1. It just happens to be negative numbers, right? So what you really have here is you have x to the negative third plus a negative 6. Yeah, so that's x to the negative 9. And if I have x to the negative 9, just like Maxwell asked me to the beginning, is it going to be 1 over something? And now, even if you didn't see it earlier, you should see it now. It is. It's going to be 1 over x to the 9. It's okay? All right. 2 more. This, again, is just property number 1. So what do I do with all my exponents? I add them. So maybe what you do instead, as you're thinking about sort of showing work or thinking about it, is that you just show what happens when you add them. You negative 1, negative 4, and positive negative 5, and positive 4, right? What do I get if I take negative 1, negative 5, and positive 4? I get what? Negative 2, that's correct. So now again, you kind of can see why we want to make sure early on, section 2, that we talked about integers, because they're going to be coming up, and I don't want that to be tripping you up. Negative 2. So this is y to the negative 2. Am I done?
No.
No. How would I write it? 1 over y squared, or 1 over y to the power 2. Yep. And what lesson would that be complete without one that was super messy and ugly like 15? Let's be real, at least they're not all like that, right?
Yeah.
They're not all. Okay, you're going to have 2 or 3 of them in your homework. The rest of them are going to be more like the ones we had before, right? But this one's messy. And there's a couple of different ways to think about it. One way to think about it is to distribute the power through to beginning with, right? Get rid of that negative 3 on the outside. Move it in. A second possibility is we could flip it, and it would be a power of 3, right? And then we can move it in. There's actually a third option, and I like this one the best, is I like the idea of cleaning up what's inside the parentheses first, kind of like an order of operations issue, and then dealing with the power negative 3 after it's cleaned up. That's what my preference is. Oh, you can definitely have negatives on bottoms and on tops. You just can move them around, and then they become positive. So I also like the idea of cleaning that up because it's going to eliminate some of that issue right off the bat. Yeah.
They can start on the bottom, but they
Yes,
can't end on the
you got it. Yes, questions could start with negatives in the problem itself, but in your final answer, you're going to eliminate that issue and move them wherever they need to go so that they're not.
So if we're doing that, would it just be, since we have to subtract, wouldn't it just be x cubed on the top?
Okay, so yes, so you're going to have x, and then I'm going to actually use the properties, right? So this is a power 1, so this should be 1 minus negative 2, right? 1 on top, negative 2 on bottom, so it's 1 minus negative 2. And then the y is 2 minus 1, because there's a 1 right here. Yeah. Okay, is that all right? Okay, so Maxwell's right. This is x cubed, and then I have y. Are you good? So over here in my problem, if I think about it now, what's inside the parentheses is x cubed y to the power negative 3. It's a lot better than it was before. I only have one x, I only have one y, and I happen to not now have any fractions at all. Okay, even if I still had some negative exponents here, that'd be okay. We're not to the point where we're dealing with that just yet. We can actually deal with that power distribution now. So if I distribute this power, negative 3 and negative 3,
So x to the -9 and y to the -3.
yep,
And then we just put it over 1?
close. I think you said it wrong, but I think you meant it right.
Oh, 1 over.
Right.
Yeah, that's what I meant.
Yeah, I thought so. So the negative exponents are going to end up shifting to the denominator. So I have y to the 9th and I have x cubed like this. Let's say for a moment, I realized I didn't have one that actually ever ended this way, and I think it's probably worth addressing. Let's say for a moment I ended up toward the end of the problem with something like x to the 6th, y to the negative 2. One's positive, one's negative. Okay? Let's say that happened. If that were the case, the x to the 6th would stay because it's already positive, and the y squared would move because it's negative. Does that make sense? And Kayla, back up in the original question when you were asking about that negative in the denominator, there's another way to think about it too that I'll mention just so that you have another option here, is that some people like to get rid of negative exponents at the very beginning. And so they move things around to start with. So they would leave the x squared on top. They would move, the x on top. They would move the other x to the top as well and make it squared. They would leave the y squared on top and they would leave the y on bottom, and they would simplify from this perspective. And then they would do the power negative 3 later on. And that's totally fine too. There's lots of ways to shift things around. You definitely will. Yes, Abby.
Why is on your answer to the right, why is it y to the negative? Is that just?
Multiplication. So we're actually multiplying 3 times negative 3. And we're multiplying this power of y is a 1. Whoa.
Well, but your answer, it says y to the 9th. I don't know if that was just.
Maybe x to the 9th.
Oh, did I write them backwards? I just wrote them backwards. I'm so sorry.
Oh,
You're right. I wrote them backwards. I don't know why I did that. That should say x to the 9th y cubed. It should. Thank you for helping me fix that.
I didn't even notice.
I'm sorry. Make sure it's right on your papers, Kenny.
So in the very beginning of that, when we're trying to subtract our exponents to get a -1, how do you know if it's going to end up on top or bottom after you do that?
They always are on top after you subtract exponents. So, take a look back here at the property itself. A to the m, I'm sorry, that's not the right one. A to the m over a to the n. What that does when I subtract those is it always makes it a, and then I subtract the exponents beside it. There is no denominator when I do this. Everything moves up and the subtraction happens. That doesn't mean I might not want to put it back in the denominator later if I ended up getting a negative number, but it always moves up when I do the
So
subtraction
if it turns
property.
out negative, then you move it to the bottom?
Exactly, precisely. Okay, any other questions? You guys are really good questions you guys are asking. Bailey?
Okay, so for one of those, we just flipped it. Or
Yes,
for 12, we just flipped it. Why couldn't we just do
You
that?
could.
Because then it would it not eliminate both of the negatives?
so no, it wouldn't eliminate both the negatives. So let me erase this just so that I have another way to sort of show it, because I'm kind of out of space. But we could flip it. So we could actually take this, and then it would be xy squared on bottom, and it would be x to the negative 2, y on top, and it would be to the power 3. But it flips it already what exactly it is, so I still end up with a negative power. It's just on the top now instead of being on the bottom.
It doesn't make it not negative.
No, because what I did was I eliminated that negative. That's what I was working on. When I flipped it right there, it was that negative I was eliminating. Okay? So could I then move it to the bottom? Well, sure I could. I could leave y on top, and I could move the x to the bottom, and then it still has the x and the y squared that were there to the power 3. There's a lot of flexibility in the order in which you do things. So if I do that, I end up now having one of the y's cancel here with one of them there. I have these x's become x cubed. So I have 1 on top. I have x cubed y on bottom. and then I can distribute my power of 3. Technically, it distributes to the 1, but 1 cubed is still just 1. And then I'd still have that x to the 9th y cubed.
Why do you redistribute the 3?
I never distributed it before when I was doing it again this time. All I did before was deal with the negative. I changed the negative 3 to a positive 3, so I didn't deal with 3, I only dealt with the negative. Now, you could even just deal with the negative 3 to begin with and just distribute negative 3 through everything. That's another option. So I say there's a lot of flexibility in the order that you do this because it's all multiplication, which means you have a lot of options actually. Okay, I definitely want to give you a chance to start. You may not want to go in order. As you're looking at some of these sitting at your desk right now, you're not going to finish in class today. You're not. Some of you have already. Damaris, are you the one who keeps working ahead? You're probably already done, aren't you?
Yeah, but I was confused.
Okay. So if you haven't started it yet, you're not finishing this. This is not a 10-minute assignment, okay? You're going to be working over the weekend. So as you're working on this problems in class today, you might start with the ones that you think you're going to have more difficulty on, so you can ask before you leave. Also, remember, the Success Center is now open, and they have wonderful numbers of hours for you guys. I mean, absolutely fantastic. And they will be there on Sunday night. They won't be there tonight or Saturday, but they'll be there on Sunday night if you have last-minute questions you want to go talk to them about, too. Or, of course, you can bring them in on Monday morning, okay? All right, so any questions before I just let you loose to start working on things? All right.
I